My name is Josh Gargan, and this is my presentation on Faraday's law. Now that we have a basic understanding of how electric and magnetic fields behave in space, we can connect all our fundamental ideas into a single universal law called Faraday's law. For a magnetic field, Faraday's law says that as the magnetic flux through a surface changes over time, an induced current is produced along the border of the surface that opposes the change in flux. As the induced current is produced, a non-Coulombic electric field is produced that curls around the surface border in the direction of the induced current. The calculations behind Faraday's law are simple when you look at it step by step. First, we start out by calculating the flux through the given surface. The calculation for flux will depend on the situation because flux is dependent on the magnetic field, the normal vector of the surface, and the area. But for our purposes, the flux will depend on the change in magnetic field. To calculate the change in flux, you can look at some time value later to see how the flux has changed. The change in flux can point in the positive or negative axial direction, and the magnitude of this value is the value of the EMF that is created along the surface boundary. To determine the direction of the induced current, you can use Lenz's law because nature will attempt to induce a current that opposes the change in flux. As the magnet moves through space, it will experience a magnetic force that will try to oppose the motion of the magnet. For our experiment, we took a magnet and dropped it through an aluminum tube to observe how Faraday's law affects the motion of the falling magnet. The idea is that the magnet will fall much slower through the tube due to the magnetic force that opposes the changing flux in the tube. The tube had to be non-ferrous because ferrous material would be attracted to the magnet and mess up the experiment. The dimensions of the tube are shown, and the average time for the magnet to fall was calculated using the program tracker. I start off my code by plugging in the known constants, creating the graph of velocity over time, and inputting my values for the geometry of the tube. Next, the aluminum tube is created as a series of rings stacked along the y-axis. Then I input the mass and magnetic moment of the magnet, both of which came from the data for Lab 3. I then create a function that calculates the magnetic field of the bar magnet using the general formula seen previously. Another function is created which calculates the value of the flux changing in time. A while loop is created which loops through the motion of the magnet. In this loop, the force of gravity is calculated for the magnet, and the induced current in the tube is calculated. Then the magnitude of the magnetic force on a ring of the tube is calculated, and added to the overall magnetic force on the magnet. Finally, the net force on the magnitude is updated, and the velocity and position are updated. As the magnet starts falling, the velocity is getting exponentially larger, but once the magnet is in the tube, the velocity levels out to a constant value. The visual shows two colors representing opposite directions for the induced current to travel. The blue represents the current traveling counterclockwise, and the red represents current traveling clockwise, as seen from above. This is because the magnetic moment is pointing in the positive y direction, and as the flux changes above the magnet, the change in flux points down, and Lenz's law says that the induced current creates a magnetic field opposite the direction of the change in flux. Using the same logic for the area below the magnet, it can be determined that the red represents current traveling clockwise. When the magnet is flipped around, the motion is the same, but the direction of the induced current above and below the magnet flips. The calculated time in the tube is about half a second larger than the experimental time, most likely due to the fact that the net force didn't take drag into account. It was hard to drop the magnet vertically in the tube, and the calculated magnetic moment from Lab 3 may not have been the actual value. The shape of the velocity versus time plot shows that as the magnet falls through the tube, the net force on the magnet is constant, and the velocity travels through the tube with a constant speed. If the resistivity of the conductor were reduced as close as possible to zero, then the current in the tube would get as large as possible, meaning the value of the current in the loop would be approximately equal to the magnitude of the change in flux. This would mean that the force experienced on the magnet would be much larger, so the magnet would fall much slower through the tube and possibly would stop moving or begin moving in the positive y direction if the magnetic force was strong enough. If holes were cut into the tube, then there would be spots along the tube where there is no induced current and no magnetic force on the magnet. This means that as the magnet fell through these areas, the only force on the magnet would be the force of gravity. So the velocity of these spots would be equivalent to the velocity outside of the tube. Thanks for watching.